The second of this trifecta of videos takes the situation that we had in the first one and tilts it on end. In this case, I put a box onto a ramp. Ramp is at an angle of 20 degrees. Mass of the box is 40 kilograms, and between the bottom of the box and the ramp, there's a coefficient of friction of 0.15. Again, I want acceleration. Well, acceleration is going to be based, just as with the last video, on net force. So the net force would be the sum of the forces, and we're concentrating on motion down the ramp. Notice I have not, as in the last video, drawn a force applied. There's no one pulling this guy up the ramp. I just set him down, and I'm going to watch him slide to the bottom. So there's got to be, if he's accelerating downward, there has to be a force in this direction. That force applied. And because he's in motion, there's a force of kinetic friction in this direction. So as in the last video, I have two forces. I have a force applied, and I have a force of friction. Getting the value of those two would allow me to get the net force, and then with Newton's second law of motion, get the acceleration. But at first blush, I don't have any information. I seem a little stuck. Well, I'm not as stuck as I think I am. Because one force I have yet to draw on my diagram is the object's weight. That weight, pointing straight down, would be the mass of 40 kilograms times 9.81 meter per second squared, or 392 newtons. Now we had said that when you have a box on an incline or something on an incline, it's perfectly acceptable to take my standard coordinate plane that looks like this and tilt it on edge, so that this becomes x direction and this becomes y, with the negative and the negative, if I want to phrase it that way. Well, according to this coordinate plane, there's my box. Gravity is like this. He's at an angle. Well, if I look closely, I see that that angle actually, as with all vectors, has an x and a y component. My y component would look like this. My x would look like that. So suddenly, by breaking down that weight of the object, Fg, into its x and y components, I have one component that lines up perpendicular to the surface of the incline, and I have one component that's directed straight down the incline. Well, guess who's the applied force in this case? Yeah, not a problem. This particular side of that triangle. Now we're going to use this side as well, but we're going to use that in a little bit. In terms of who's my applied force that we didn't seem to have any information on, it's actually a component of the object's weight. Now to find that component, we have a little help from geometry. That 20 degrees on the incline is actually the same angle as I find right here. Oops. Right there. That angle is 20 degrees. With the value of the hypotenuse of this triangle being 392, and this side that I'm targeting being the opposite side of the angle, well, 392 sine of 25 degrees is actually my force applied in the quote-unquote x direction. It's really as straightforward as that. It's just a component of the weight of the object, not the full weight, not at all, but definitely a component. And if I go ahead and find that value, he turns out to be 134 newtons. So, force applied, 134. Yay! Unfortunately, that still leaves a force that I have to work with, and that's the force of friction. Well, I have a formula to deal with force of friction, and I have already at least one piece of information for it. and that's the coefficient of friction, which is the ratio of the force of friction to the normal force. Just as in the last problem, I've got to find that normal force. Well, the direction of the normal force is still defined the same way. It's defined as the force applied perpendicular by the surface onto the object. But now my perpendicular to the surface is not exactly the same direction as it was in the last problem. But breaking him open is really, again, not that bad if I think about it. If I go back to this, where I had my box and I had my weight, I said that this other side of the triangle, this guy right here, would come in handy. Because if I look at it, this particular side of, this particular force is your normal force. That component of the object's weight right there is exactly in the opposite direction of the normal force. So barring any other forces acting in the y direction, that is going to be the value of the normal force. Well, to find this side of the triangle, we use the sine function. To find our desired side of the triangle, we use the cosine function. So 392 cosine of 20 would actually be, in this case, equal and opposite to the normal force. And I wind up getting 369 newtons. Now with that in my pocket, I can go ahead and work my formula. 369, oops, stumbled there a second, coefficient of friction, 0.15, force of friction, 55 newtons. Now, I can't forget it is opposite the direction of the motion, so I'm going to make him negative. My net force winds up being a whopping, what was it, 79. Well, now I'm all ready to go into Newton's second law of motion. 79 newtons is 40 kilograms times acceleration. Acceleration winds up being 1.98 meter per second squared. So there was a twist in this particular problem. He's on an incline. That does change the way a little bit I approach my calculation of the normal force, and therefore my calculation of friction. But the knowledge that I can turn my coordinate plane on end, that I can go ahead and without any fear of repercussions, make it like this, where I have x, x, y, and y, actually facilitates the problem solving. Because all my forces, friction, the applied force, which is a component of the object's weight, those are now all acting along the incline that I've defined as my x-axis. The only guy that's at an angle to that was the weight. So in terms of working with vectors, I only had one vector I had to resolve into my x and y components. If I had left my coordinate plane as it had been, if I had kept it like this, with the weight nice and straight down, isn't that lovely? Unfortunately, my box is sitting there like this. Force here and force here. I'd have to resolve both of those into components. It would wind up being a mess. So with a problem where you have something on an incline, tilt that incline, tilt the coordinate plane to match the incline. The inclined surface is the x direction, perpendicular to the inclined surface is the y, and go from there. Next problem is going to be a little bit of a doozy.